Hello students, this is the simple tricks to write Haworth structures of different carbohydrates. See here one simple monosaccharide carbohydrate cyclic structure of glucose. Here a glucose molecular formula is C6H12O6. In cyclic structure we can write 6 carbon atoms like 1, 2, 3, 4, 5, 6, and that oxygen bond linkage takes place here at a C1 carbon atom and at a C5 carbon atom. OH, OH, H, OH, and here oxygen atom is linked with this carbon atom OH. Where there is a OH group, that is right hand side, this is the RHS. Left hand side LHS hydrogen atoms are present. See here OH, H, H, OH, OH, H. Then it is linked with this carbon atom OH and H. At a C1 carbon atom, OH is present right hand side, that is alpha form. At a C1 carbon atom, OH is present left hand side, that is beta form. These are called anomers, alpha and beta forms. Okay. These cyclic structures was introduced by Fischer, but in examination they'll ask, draw the Haworth projection formulae for any carbohydrate. To write the Haworth projection formula for any carbohydrate, that is generally 6-membered rings. In organic chemistry, one compound pyranose is there. 6-membered rings are generally called pyranoses, alpha glucopyranoses. So by using these in examination to remember H and OH groups to represent at each carbon atom, it is very difficult. That's why here one simple trick for glucose related compounds like maltose, lactose, sucrose, amylose, amylopectin, cellulose, almost all are with this a simple trick easy to write. That is, below the plane of this carbon OOHOH, just remember OOHOH. This O at a C1 carbon atom, O represent OH. At a C2 carbon atom, O represent OH. H represents H only at a C3. O represent OH at a C4. Here H represents H only at a C5. Okay. Anyhow, draw the simple hexagon like pyranose like this. Once we can observe this Fischer cyclic structure, that oxygen bond linkage is present at C1 and C5. Here also in this see here, this is the, I'll consider this is C1, this is C2, this is C3, this is C4, this is C5. Now here see here in this structure at a 6th carbon atom CH2OH is there. Right here same thing, here 6th carbon atom CH2OH, that is the common. 6th carbon atom is clear. Now follow this formula. Below is nothing but this is the one line passes through this. This is the above the plane and below the internuclear axis like. Now at a C1 carbon atom, OH group is present, OOHOH. Simply write OOHOH. Clear? Now, where there is a OH, opposite side H groups are present. Without any confusion, easy to write. See here, at the first carbon atom, all right hand side groups are below the internuclear axis. Left hand side are above the internuclear axis. Now same based on this only one simple formula is below the plane OOHOH. Based on this we can write like at a C1 OH, C2 OH, H, OH, H. Here OH is there na H. OH is then opposite side H. H is there opposite side OH. OH is there, this is H. Finished. Now this is alpha form. Alpha D plus glucose. That is called alpha D plus glucopyranose because it is a 6-membered ring. Same similarly, if they'll ask a beta form at a C1 carbon, that is the functional group carbon atom only differs. So here at a C1, here in alpha form OH is this, but just change this. Here OH and here H, remaining everything is same. And don't create one more formula for this, just remember only one. Just alpha and beta only differs at the first carbon atom only. Now here common it is OH, this is H, this is OH, this is H. Fifth carbon atom and it is sixth carbon atom CH2OH. Now opposite side, OH is there na, here H. H is there na, OH. Here it is H. Now this is beta form. Now this is called beta D plus glucopyranose, 6-membered ring. It is very simple to remember to write Haworth structures without any confusion and without any missing functional groups H and OH groups. Okay students, the next, so here same related maltose. So here maltose is a disaccharide reducing sugar. Here 2 moles of alpha D plus glucopyranose condenses, it gives corresponding disaccharide, that is maltose. Two same groups are there na, apply the same formula, that is OOHOH. So here I'll write this is C1 OOH OH. Clear na? Opposite. This is H. This is H. This is OH. Now this is H. Now fifth carbon atom. Obviously this is sixth carbon atom CH2OH students. Then again here like O H here O here H. Fifth carbon atom. Sixth one is CH2OH. So here students, this is C1, add this H, this is H, this is OH, this is H. Now between these, just one rough idea, condenses means water molecule easily liberate. From here hydrogen atom, from here OH group eliminate, it gives corresponding disaccharide, that is maltose. That is linkage takes place at C4. Now we can write for this direct linkage, we can take like oxygen and this. That linkage takes place between C1 of one and C4 of another glucose. That's why it is called a alpha C1 C4 alpha before or after that alpha glycosidic linkage. Glycosidic linkage is present. So in examination in maltose, what type of glycosidic linkages are present means this is C1 C4 alpha D plus glycosidic linkages are present. Very important. It is a very simple trick by using this OOHOH. Same similarly, see here students, lactose, it is a disaccharide reducing sugar, and it is the combination condensation of beta D minus galactose and beta D minus glucose, it gives a lactose. It is very simple. We know the formula OOH. But here there is a slight difference between galactose and glucose, that is at C4. In glucose molecule at C4 here OH is below, we know OOH formula according to this. But here in galactose at C4 opposite in position, just reverse. There is slight difference between galactose and glucose. Remaining everything is same. See here, we know the formula beta D plus, we know beta form. This is here only difference. Here H, here see here the difference. Here H and here OH. Remaining everything is same. O H O H. Then it is CH2 OH is common. Then here H, then here OH, here H. Now it is also a beta form. Beta form means we'll take here OH group. Here H. Formula is same. OOH. Here changed. Here H. Here the CH2 OH. Now glycosidic linkage takes place between C1 of beta D minus galactose and C4 of beta D minus glucose, means from here hydrogen and this linkage takes place. Right, directly like this linkage takes place. This is C1 C4 beta D minus lactose, that is glycosidic linkage takes place here. It is very simple to remember all these structures here. Alpha D plus glucopyranose beta form, then here it is maltose, both are same, glucopyranose is only. Then lactose, one is galactose, another one is glucose. Only by using the simple formula, that is OOH. Easy to write Haworth structure for glucose, maltose and lactose. And based on this, see here students, based on this I'll give one more important, that is polysaccharide, that is starch. Starch is the polysaccharide. Now it containing two components. One is amylose, another one is amylopectin. So here amylose is a water soluble component, easily soluble in water, and it containing approximately 15 to 20% glucose component. It is unbranched with 200 to 1000 alpha D plus glucose are present. That glycosidic linkages takes place at C1 and C4. Now amylopectin is water insoluble, 80% glucose is present, branched chain polymer it is. There are two important glycosidic linkages are present, that is at C1 and C4 long chain unbranched, at C1 and C6 branching occurs. Now here in starch containing alpha D plus glucose is only. Alpha D plus glucose, we know formula directly. That formula we know, that is very simple. Formula shortcut is, we know, that is OOH. We know formula. Now it is OOH. Now this is CH2OH. Very simple now students. Now here hydrogen, here OH, here hydrogen. Now again OH. Now it is CH2OH students. Then again here, see here OH, this is O and it is H, here the CH2OH. Then right opposite side here OH is there now, here H, here OH, here H, same here, like H, here OH and here H. Now and so on, this is, and so on, this is. Now between these glycosidic linkage takes place, between these condensation due to the condensation glycosidic and so on. Here there is a one linkage, here there is one linkage, that is C1 and C, this is C1 and it is C4, C1 C4 glycosidic linkage is present, just like it is a maltose linkage present without any branches. Now see here amylopectin, same formula, OO HOH. Now here also same formula, OO HOH, formula OO HOH. Now here CH2OH because it is sixth carbon. Now it is H, here OH, here H, here H. Now a sixth carbon atom CH2OH, here H, here OH, here H, here H. Same here, here H, here OH, now here H, here H. Now it is a, just already had explained, amylopectin is water insoluble and branching takes place at a C1 and C6. Now C1 of this carbon at this carbon atom alpha D plus, and one more link up takes place, just like here link up given, see here, this is like at a sixth carbon atom link up takes place, C1 of one, C6 of another one, that is branching, C1 C6 branching takes place. Now this is common, C1 C4, C1 C4, it is a unbranched continuously polymer chain takes place. This is C1 and C4 glycosidic linkage takes place. Now it is clear, amylose and amylopectin. So if they'll give any starch components like amylose and amylopectin, easy to write its structure by using only one simple formula, that is OOHOH, like. Then one more is here cellulose. Cellulose is a polysaccharide, but it containing beta glucoses and a form beta D plus glucose form, and branching at C1 and C4 glycosidic linkage takes place. Try this, students, otherwise I'll explain next video. I'll clear the doubt for this structure or the structure for cellulose. Just try this. Then see here one more simple example is fructose. Formula is same. Fructose and glucoses both are having same molecular formula, fructose and glucoses. Only difference is in glucose CHO group is present, aldehyde group, it is containing C double bond O carbonate ketonic group. Means ketonic and aldehyde both are having same molecular formula but differ in their functional group. That's why these two are the best example for functional isomerism. Now see here also one shortcut created. Below the plane now, to write the 6-membered rings, we want OH, OOH at a C2, C3, C4, C5, C6. But here in sucrose molecule, we don't want a 6-membered rings, we want a 5-membered rings. They are the furanoses, furans like. So for this below the plane, there is one simple shortcut is, remember this only, OH and OH only. So in sucrose, fructose exists as a 5-membered ring, that is a furan. So here students, I'll take here simple structure for fructose 5-membered rings, that generally here one simple open chain structure I will explain. Fisher structures here, students, for fructose based on functional group, and here one cyclic structure given at a second carbon atom and at fifth carbon atom. Linkage takes place at second and fifth carbon atom. Just like in glucose, OH group is present on right hand side, that is alpha form, and OH group is present on left hand side, that is beta form. This is LHS. Same thing. So based on this, here also it is very difficult to write 5-membered rings. By seeing all this, little bit confusion. That's why better you remember this simple trick is OH. So here that oxygen bond linkage is present between C2 and C5. So here this is the C2 and this is the C5. Here also see here C2 and C5. See here at C2 carbon atom above and below. Here given a shortcut node. See here OH. Now here at second carbon atom, O stands for OH. Then third carbon atom is H. Then fourth carbon atom is OH. Then fifth carbon atom is H. Here the second carbon atom is there. We want first carbon atom, that is CH2OH. First 1, 2, 3, 4, 5. Now here also CH2OH. Clear. Sixth carbon atom it is. Now it is alpha form, because at C2 carbon atom OH group is present below the plane. That's why it is a alpha form. So same thing, if you want to beta, only difference is at second carbon atom. Here OH group and here CH2OH. Now 1, 2, 3, 4, 5. Here CH2OH is common. We know formula OH. Now where there is H, opposite OH. Here H. Same. Here also OH. Now here H. This is the beta form of fructose. We know this beta form because in sucrose we want beta D minus fructose and alpha D plus glucose. To write that sucrose molecule, it is a non-reducing sugar. See here, it is a non-reducing sugar. To write that disaccharide non-reducing, we want one alpha D plus glucopyranose and beta D minus fructofuranose to get a sucrose molecule. We know one shortcut na for alpha D plus glucopyranose, students, that is at C1. Formula is what? OH. This is 1, 2, 3, 4, 5. Then it is a CH2OH, sixth carbon atom. Now add this H. OH is there na H. H is there na OH. OH is there na H. Very simple. Then here in fructose, it is a beta form. Now at a C2, it is CH2OH. We know the formula H, OH. This is the CH2OH because it is sixth carbon atom. Now it is OH. Now between these condensation takes place. Now there exists one linkage that is called here C1 and C2 of glycosidic linkage exists. Why it is called a non-reducing sugar is nothing but at C1 carbon atom of glucose, here the CHO group, aldehyde group is present, and in fructofuranose at second carbon atom C double bond O group, like a ketonic group present. Both are connected with this glycosidic linkage. Both are participated in this bond. They are not free to reduce the molecule, sucrose molecule, or means it is non-reducing sugar, do not reduce failing solution, Bendix like. Because at a C1 and C2 carbonate, functional groups are not free to react with the respective suitable solvents. Now, by using this is a simple shortcut OOHOH and OHOH, we can write easily all carbohydrates over the projection formulas.